Let's implement the blink ability in this topic, which straight up teleports your character to another location. This is one of the most overpowered abilities in any video game. So by my game design, we will use a small delay before we teleport to that location. Yes, it has indeed been quite a while. Welcome to the 5th chapter of this gameplay ability system series. In the part 1 of this topic, we will just work on the basic functionality of the blink ability. I've created the blink ability in the ability system, abilities, and the anti-mage folder since it represents a specific hero's ability in Dota 2. As it always goes, you can create a blueprint ability derived from the gameplay ability class. So currently, this is what my blueprint ability blink looks like. First, you set the properties, all necessary tags. Make sure to include other ability tags as well to cancel and block them from activation. And ensure this ability has its own asset tag, preferably unique, so it can be easily identified. And just in case, it's better to have a silence tag to prevent this ability from activation. Ensure you've set the right values to this class properties to enable the retrigger instance ability. We will need it, as you will see later in this topic. Notice how I have ability triggers set up for this ability? Yeah, that's right. We will be triggering this ability in 2 different contexts, just like the dash ability in topic 3.3, where we executed the ability using ability triggers for events, combat dodge, and movement sprint. Likewise, our blink ability will execute for 2 contexts for targeting and confirming using gameplay events. I've also created effect classes for cost and cooldown. Cost being instant, consuming mana for 20 points, and the cooldown effect being a duration effect, obviously, for 3 seconds and grants the movement.blink tag. I've created new gameplay tags. In the JSON files stored in the tags folder, the tags movement JSON file has a new movement.blink tag used as an identifier for that action. The tags queues JSON file has the gameplay queue tags for parry, stun, root, and now blink. The tags ability JSON file has the tags for ability slots 1, 2, 3, and ultimate. I've also added a couple more tags for the ability targeting and confirming. And now it's time to import these tags into the editor, which has already been done using these data tables for each of the gameplay tags JSON files. Now in any one of your data table, you can just re-import a tag by pressing the re-import button. And this can be validated in the project settings in the gameplay tags section. You may have already imported as many data tables for your gameplay tags. For this movement data table, notice how you'll find your newly added tags in the tag hierarchy. If you do the similar steps for other tags as well, you should see your newly added tags. Any new tag can now simply be re-imported since the data tables are already added to this gameplay tag table list. For example, if I delete this blink gameplay queue tag, you can see the absence of this tag in your project entirely. However, re-importing all tags in this data table will bring in new tags from those JSON or CSV files being used by that data table. Likewise, as another example, let's go ahead and delete targeting and confirming tags from the gameplay tags ability, and it can be confirmed in the project settings gameplay tag list. And simply re-importing in the data table can include the newly added tags in the raw files of JSON and CSV. Now it's time to invoke the ability with inputs in the player controller. Instead of the base, SRC, and game folder, open up the base player controller BP class. If you have been following along, you may have already implemented the inputs of other abilities. In this combat section, I have inputs for both melee and block with left and right mouse buttons. In the movement section, we have inputs for movement abilities like jump, sprint, dodge by querying for their ability slots, and dash as well, where we send a gameplay event for the context of dodge and a tag to end the ability. And after a certain delay, we can send another gameplay event for the sprint context, effectively making the same ability operate on different contexts, and all of this happens locally. In an empty space in the base player controller class, add a new debug key event for the letter Q. This will be used to send the events to the control pawn for targeting. Using the ability.target.targeting tag that we just added, and this event shall fire when we press the button Q. For this demonstration, let's confirm the target location using the event tag ability.target.confirm, and that shall happen on the release of the button Q. So when Q is pressed, the player's pawn will be targeting, and on release, the player's pawn has confirmed the target location. This is my existing implementation of the blink ability for this topic. For this implementation, I've overridden and implemented the event activate ability from event, which has a parameter event data for use, where I can query for any value pertaining to that event, and not the typical activate ability function that we've been overriding and implementing all along, which is where we can get the event tag that triggered this ability. Now let me first attempt to print a log message for this event, blink targeting, and likewise, let me log a message for the confirm event, blink confirmed. Let's compile and save and test this basic functionality. Let me play my level. You will notice the log message targeting, and after I release, the other log message confirmed. And once again, targeting followed by confirmed. Although we sent the event locally, the ability was activated on both server and client, unlike the wait gameplay event ability task. So any ability bound to that event can be triggered, so generic tags can fail, generic tags can be harmful, and so it's better to have separate tags for each ability. We need to have this property enabled, retrigger instanced ability. Let me show you the fail case if this property was false. The ability is active just once and never confirms, because the ability is still active. So that's why having this on means you can retrigger an active ability. That's why you can end the ability and have it activated again for another event. Now that we're through with this topic, we can move on to the next section. It's like in most games, how you have a certain emitter or see-through material where you want to cast something into your world. We will be implementing the aim and targeting logic for this event, obviously, but for this demonstration, I will be using a looping function to show a debug capsule. But ideally, you want to be showing an actor with a translucent material to see through into your world. I have stored the timer handle in a variable. The looping function is showBlinkLocation, which we will execute before the looping delay. Ensure that it is looping for a small delta time of 0.02 seconds or world delta if you wish to. Since this targeting event can happen locally, we can ensure that this is locally controlled. And now it's time to implement this showBlinkLocation method. It's a simple void function with no parameters. That's what timer handles in Blueprint operate on. And we will perform a series of operations. You could do it from the player or avatar actor's location, but I wish to do the tracing from camera so that the location is very camera bound, if you will. We will get the first player camera's manager object, its root scene transform component and its world location, and store it into a local variable blink target start location. Next, we will make the blink target location using a new method and store that output result into another local variable blink end location. So now we have both local variables for the start and end blink locations. The last step of this function will be to draw the debug capsule itself. We will be doing it for the duration of 0.1 seconds, the radius of 30, and half height of 80. The center of the debug capsule will be the target location itself, so we'll pass in the blink end location to this parameter. Now let's begin the implementation of this function, make blink target location. We will continue to use the location of the player camera manager of the first player and use that as the starting location. The end location must be the addition of the start location vector and a magnitude of its forward vector. For an actor in the world at a certain location and a forward vector, a target in that direction at a certain magnitude distance can be obtained as a magnitude factor of that forward unit vector. This is an offset of the position vector of the starting location. Think of the target location to be anchored to the start's world location. As part of your further reading, you could look up unit vector and position vector. So let's just do that and multiply that with a certain blink range. This blink range can be made a property of this ability, like in Dota 2, or a blink or dash range attribute for your ASE character. I have used a default value of 700, and you can have different values for different ability levels. For a character and a target object at a certain distance, if we are calculating the target location relative to the camera location, we want to effectively remove this distance. Yes, an even better way to do this is to get only the forward vector from camera and add it to the world location of the control pawn. And so the target location is relative to your character, as it should be. So now we can get this distance node to get the distance between two vectors. They would be the starting locations of the camera and the control pawn. So let's get the root scene transform component starting location and the actor's world location. And let's use the xy values of the vector. X is for the distance from the character, y is for the distance from the shoulder, as in over the shoulder third person cameras. That effectively removes this distance between the camera and the character. Now, adding this distance with the blink range, we can get the correct magnitude from the character. That will be factored with the forward vector and added to the starting location to get the final and effective blink location. So this completes this method, and the blink end location is calculated in this show blink location method in every periodic tick in this timer handle function, effectively calculating the right end location every delta seconds. Now, we need to find the blink hit location if there was a line hit trace. So let's collapse this function for better readability. I made it a pure function since it only does a simple calculation. As part of the next step of the sequence, we can get the hit result in this method itself. Using capsule trace by channel blueprint node, we can keep the same radius and half height as a draw debug capsule. Let's make sure to ignore self. Let's pass in the start and end locations we just calculated. And as a safety measure, let's also add our pawn to the list of actors to ignore. Now when we break the hit result, if there was indeed a successful hit, the blink end location will be this location value. If it is false, the blink end location will remain the same, a simple target location in space. This completes the calculation, and finally we can return the calculated blink end location. Now this method can keep running in a loop every delta time. Now in my client 1, when I press Q, I can see the target location in space, and on release, blink confirmed. Once again, the server can't see or operate on my blink targeting, and on release, blink confirmed. First, let's disconnect the exec pin from the print, and as part of the first step, let's clear and invalidate this timer handle, which is technically the timer handle that should end since we're not targeting anymore. As part of the next step, let's do a last and final calculation of the blink target and store its output in a variable. This is indeed calculated on both machines, but the server will be incorrect. Let's print the log and see it for ourselves. As you can notice, the client and the server's locations vary. The server's location is quite incorrect, and that's not technically the location we want to blink to. The incorrect location comes from this part of the calculation. Since we're getting the first player's camera manager, the server will get its own player's camera. So technically, the server blink location is this guy's shoulder, since it is the added distance of the camera and the character's world location. Let's also quickly commit the ability so that we can apply the cooldown and cost soon after confirming the ability. Soon after the blink confirmation, as you can see, the cost has been applied, and I cannot activate the ability until the cooldown wears off. This brings us to the next section, Blink Portal at Target Location. As in topic 2.3, we need to execute gameplay queues. We need to use this method, execute gameplay queue with params on owner. The first parameter is the gameplay queue tag, identifying the gameplay queue class itself. For the second parameter, we can make the gameplay queue parameter struct. This struct accepts a location value for which we shall pass the latest calculated blink location. So now we are packaging our calculated blink location into the gameplay queue parameters and using these parameters to execute the gameplay queue of tag gameplay queue.blink. I have stored this gameplay queue particle effect in the folder ability system, queues, and blink. This is what the particle effect looks like. If something disappears or fails to load, just press the restart level button and the particle effects will reload correctly. This particle effect in question is got from the Paragon Gideon's assets. Let me apply the cascaded particle system filter and search for portal. And this is the portal effects used for the blink gameplay queue. So make sure to create the blink folder first and then just copy paste this asset into the new folder alongside the gameplay queue classes. I will show you either types of gameplay queues. For now, just subclass from the static gameplay queue blueprint class. You will want to override the onExecute method from other virtual methods. In the sequence of operations, I will use the simple particle spawning method spawn emitter at location. This expects an emitter template, which would be your FX blink itself. Now, breaking the param struct reveals the location property, which is indeed our effective target location where we want this particle emitter to spawn. Now let's return from this ability with the parent class's function's output value. Set the tag gameplay queue.blink for this gameplay queue class. Now the engine will track this class for this gameplay queue tag. Simply using a gameplay queue tag here will allow the engine to use the gameplay queue class bearing this tag and will execute your gameplay queue functionality. When I confirm blink on this client, the server has an incorrect location as expected. Like I had mentioned, the location will be on his shoulder, accounting for that distance between the camera and the character. For the player camera manager, 0. Since in every machine, the camera manager 0 belongs to the first controlled pawn itself. Just like this static gameplay queue class, we can create an actor gameplay queue blueprint class. This has the same implementation for onExecute method. It shall use the same blink effects and the same parameters. For the gameplay queue tag, we shall remove the tag in the static gameplay queue class and reuse the same tag in the actor gameplay queue class. And now, when I play my level in the viewport and filter with blink for an actor, you will notice a gameplay queue actor blink actor in the level. But for the same machine, it has created only a single time. So GAS makes sure that there can only be one same gameplay queue actor for a machine. Similarly, for the client machine, there will only be one gameplay queue actor in the level for each machine in the session. So the advantage to a gameplay queue actor is that, just like an actor, you can work on many lifetime events and methods like end play, destroyed, on actor clicked, any damage events. And it is quite unlike the static class, where even after using this gameplay queue, there isn't a creation of this gameplay queue as an actor in the level, no matter how many times invocation or even on the server. Now let me attempt to print a log message in the execute function, and you will notice the print happens on all machines. Because a gameplay queue is indeed a net multicast RPC, so the server will have it executed on all machines. And with this, we end the section on Blink Portal at target location. We shall continue this topic as another part in the next video.